I would like to discuss with you another type of algorithm, a quantum search algorithm. This was also on the last problem set, but I think it's quite instructive to discuss how such an algorithm works in principle, so I would like to do it here during the lecture. It's a very, very simple case. It's not the general quantum search algorithm. There's a quite a well-known algorithm, as Grover's algorithm. I will not go into that, but I will limit myself to a very simple example, which, however, shows the basic idea behind such search algorithms. Often you are looking for the solution of a problem, and finding the right solution is difficult. But if you have a proposal for a solution, checking whether that proposal is correct or not is simple. Now imagine that you have a problem where you have n possible solutions and you want to find out which is the correct one. And you can, of course, you could do that with trial and error. So you just go through all the solutions, try them out, and check whether they are correct. So we assume that checking whether a solution is correct is rather simple and straightforward. So you could just go through all the possibilities until you find, and check them all until you find the correct one. And doing so would the number of checks that you would have to do would scale linearly with the number of possibilities. And here I would like to show a quantum algorithm which works, which finds the solution faster than that. I will limit myself to the simple case where you have 4 possibilities. So 4 possible solutions to your problem. And say all solutions are equally likely, then if you were looking for the right solution classically, then on average, you would have to check 2.5 solutions. So you have 4 possibilities for the number of times you have to try. From 1 to 4, they are all equally likely, and the average number of trials would be 2.5. Now, here is a proposal how you can do that faster with a quantum algorithm. And like previous algorithms that we looked at, this algorithm works with an oracle. And here the oracle is denoted by the O. It's a 3-qubit gate. And it works as follows. You have 2 so-called data qubits. We encountered that also in earlier oracles. And they encode the query in the sense that we have 4 possibilities for our solutions. We want to check them. And we can label these possibilities in binary representation. These would be 2-digit labels from 00 to 11. And practically the 4 different basis states of these data qubits, they label, they encode the 4 possibilities for our solution. These data qubits, as long as they are in basis states, they remain unchanged, as was the case with our previous oracles. Then we have a target qubit, T, and the oracle works in such a way that the target qubit is flipped if and only if the solution label encoded by the two data qubits is the correct one. So if the data qubits specify the correct solution, in that case, the target qubit is flipped, and that is denoted once again with this addition mod 2. And what you add, that is the product of two Kronecker deltas, delta xj and delta yk, where jk label the correct solution. So if our data qubits x and y coincide with the correct solution, jk, then the target qubit is flipped. So this is our way of checking via an oracle whether a proposed solution is the correct one. And now the quantum circuit that searches for the correct solution looks as follows. I give you immediately the full circuit, and then we will check step by step whether it does what I promise. So we have 3 qubits coming in, the first 2 in basis state 0 and the third one in basis state 1, and they all go through Hadamard gates. We've seen that in many circuits before. And then they enter the oracle. So you recognize a basic feature that we've seen before, that we don't go into the oracle with basis states, but we prepare superposition states, and then we enter the oracle with superposition states. After the oracle, basically the last qubit, the third qubit, has done its share, and nothing happens with it anymore. So we can basically ignore it after the oracle. And the 2 data qubits, they undergo yet another Hadamard transformation. Then they pass through a specific 2-qubit gate, which I will explain in detail in a minute. So it's not yet specified. It's a particular 2-qubit gate labeled V. And then yet 2 more Hadamard gates, and then a measurement in the standard basis for both data qubits. The claim is that the measurements at the end will give you the label of the correct solution. So you have to run it only once, this circuit, and you get immediately the label of the correct solution. So here's a blow up of this 2-qubit gate V. It's actually composed of several elementary gates that we recognize. So both qubits first go through Pauli X's. Then the lower one goes to a Hadamard. Then we have controlled NOT, another Hadamard for the lower qubit, and then at the end 2 more Pauli X's. So here it is. This is the blow up of this 2-qubit gate V. And let's try to understand what that gate does. First of all, we can simplify matters by recognizing that this combination here at the center, that was a very early homework problem. That is effectively a controlled Pauli Z. And then in order to understand what this circuit does, we can look at the matrix representations of these respective gates. When 2 Pauli X's act on each of the qubits, then in terms of matrices, this is described by such a matrix. So it's a 4x4 matrix because we are in 2x2 in a 2-qubit Hilbert space. And each entry of the matrix is a 2 by 2 matrix. So in the off diagonal, you have Pauli axis. You can convince yourself that this here corresponds precisely to the action of two Pauli axes in parallel. And likewise, at the other end of the circuit, you also have the same matrix representation. Now, in the middle, we have a controlled Pauli Z, and such a controlled operation is described by a matrix where in the upper left you have a 2 by 2 unit matrix, and here you have the Pauli Z, and the off diagonals are 0. So this is the action of the circuit in terms of matrices in the standard basis. And when you multiply these matrices, then you obtain this form. Pauli Z is diagonal with entries 1 and -1, and it's sandwiched between two Pauli axes. And what this sandwich does is it flips the order of the two eigenvalues, so that you have in the top left the -1 and then the 1. Yeah, so this is the Pauli Z, but with the order of the two eigenvalues flipped. And then you have in the lower right the unit matrix, so the rest is 1 and everything else is 0. So you can neglect the overall sign. You can say this up to this overall sign. You can also view this as +1 and the rest is a -1s. And this means you can consider this as 2 and the rest 0 minus the unit matrix. So up to an overall sign, this is another way of writing this matrix. The first of these two matrices can be regarded as 2 times the projector onto the basis state 0, 0. And the second matrix, of course, is the identity. To summarize what this circuit does, we defined this as our 2-qubit gate V, and the unitary operation that is effected by this gate is up to an overall sign, which we don't care about, is 2 times the projector onto basis state 0, 0 minus the identity operator. So this is something we should keep in mind when we go through the circuit and when we encounter this particular gate. So let's start with the circuit, and let's consider the first transformation that leads to the state psi1. And it's we have Hadamard's applied to the 3 basis states coming in. This is a situation that we've encountered before, so it's quite straightforward to write down the state psi1. It follows the same logic as in previous examples. The psi1, that is the Hadamard transformation applied to the 2 basis states 0, and we encountered in previous examples, we encountered a nice representation for the transformed state. Namely, we can write this as 1 over 2 to the power n half, where n is the number of qubits, but here it's 2, so it's 1/2. And then we have a sum over x, where x is a bit string of length 2. So the sum over all possible bit strings of length 2, and then the basis state associated, the 2-qubit basis state associated with that bit string. So this first part, that is the Hadamard transformation of the 2 data qubits that were previously in the basis state 0. Then we have the target qubit, which was initially in the basis state 1, and that is transformed into a minus state by the Hadamard gate. And the minus state, that is 0 minus 1 over square root of 2. So that's the state after the initial Hadamard gates. Then all 3 qubits go through the oracle. When the data qubits are in basis states, then labeled by some bit string, then the oracle flips the target basis state if and only if the bit string labels the correct solution. So let's say the correct solution is labeled by a bit string x0. Yeah, so it consists of 2 bits. Now, what we can do is we can split this sum into 2. We can first take the x0, which is the correct solution, and then the sum of all the others, all the incorrect bit strings. When I have the correct solution, x0, then for the target qubit, the basis states are flipped, and 0 minus 1 becomes 1 minus 0. For all the others, so then I have a remaining sum over all x's which are incorrect, so they're different from x0. For all the others, the target basis states are not flipped, so I keep 0 minus 1. Okay. Now up to numerical factors and overall signs, we can factor out 0 minus 1, which is the minus state. And for the 2 data qubits, we have x0, and then here we have a relative minus sign, minus the sum all the other x's, basis state x. At this point, the target qubit has served its purpose, and from now on, we shall forget the target qubit, and we will with the state of the data qubits only. In the next step, the 2 outgoing data qubits pass through Hadamard gates again. And here we use again a result that we had used for previous examples for the action of a Hadamard transformation on an arbitrary basis state x. If you remember, that could be written as the sum over bit strings of length 2, which I now call z, and scalar product of z with x0. Yeah, so this is the action of the Hadamard gates on x0, and we have the same also for all the other x's. So they have a sum over again over z, and x different from the correct solution. The power scalar product bitwise mod 2 as z with x, and then basis state z. And then we can take out the sum over z, and we can also take out the basis state z. And what's left in the square bracket is the -1 to the power z dot x naught minus the sum over all the other x's -1 to the power z dot x. Okay, so this is the state after the next round of Hadamard transformations. Then comes this peculiar 2-qubit gate V, giving rise to psi 4. So that is V applied to psi 3. And remember what kind of unitary transformation that's effected. That was 2 times the projector onto basis state 0, 0 minus the identity. So this leaves psi 3 unchanged. This projection picks out of this sum of all z, it picks out z equal to 0. So this first part here will give something proportional to basis state 0, 0. And the prefactor is, first of all, this factor 2. And then from this square bracket, when z is equal to 0, then we have 0 in the exponent. So this is 1. This is also 1. Now here we have 3 out of 4 incorrect solutions. So this gives 1 and the sum gives 3. So we have 1 minus 3. In total, this is a prefactor minus 4. Then we subtract from that this whole state. So I have to write it again. There's nothing I can do. This is our psi 4. After psi 4, after the this 2-qubit gate V, the 2 data qubits yet again go through Hadamard gates. And this gives us the state psi 5, and this is the last step before the measurement. First, we have here the Hadamard gates applied to basis state 0, 0 with a prefactor minus 4. And there we use yet another time our nice representation of the effect of the Hadamard transformation on the basis state 0, namely 1/2 sum over all bit strings of length 2 and basis state x. What about the effect of the Hadamard gates on the remaining sum? Well, if you remember, this representation was actually the effect of a Hadamard transformation. And now by applying Hadamards again, we are basically undoing the original Hadamard transformation. So we are going back to the state x0, and here with if I multiply out the bracket, the state X. Yeah, so basically we are reversing the original Hadamard transformation. However, along the way, there's a numerical prefactor, a normalization factor that we have to take into account. It's a factor of 2. Yeah, so this is necessary to get the right normalization. We can split the first sum here in 2 parts, as we did at the very beginning of this algorithm. So we can split it into x naught and a sum over all the others. And then from that we subtract 2 times x naught and we add the sum over all the others, x with a factor of 2. And what you see is that the terms containing the incorrect solutions, so the basis states corresponding to the incorrect solutions, they cancel out. So up to possibly a sign, yeah, the state psi5, the final state before the measurement, is actually the basis state x naught corresponding to the correct solution. And then it's clear that if I perform a measurement in the standard basis, this will give me precisely x0, so it will give me the correct solution. Okay, so this is once again the circuit, and we showed that indeed with one run, and in particular one query to the oracle, you can immediately find out the correct solution. This is a good point, yeah, that you raise, the similarities and the parallels with the Deutsch-Doscher algorithm. There are, in fact, a lot of similarities. I mean, the oracle here has the same structure as the oracle in Deutsch-Doscher, only that here the binary function has a very particular form. It's basically an indicator function. It's 0 if the argument represents the wrong solution, and it's 1 if the data qubits represent the correct solution. So it's an oracle it's the oracle like Deutsch-Doscher, but with an indicator function. Also, another parallel is the Hadamard transformations before and after the oracle. Yeah. Also, the data qubits going in basis state 0, the target qubit going in basis state 1. So this is basically running like Deutsch-Doscher, and then comes this 2-qubit gate V, and this is really a peculiar feature which deviates from Deutsch-Doscher. And the unitary transformation that this particular gate V effects contains this projection onto the basis state 0. So this is what really makes this circuit peculiar. And it's also a feature that is maintained when you go to more general search algorithms, like the Grover search algorithm, that also contains a step which does a projection like this one here. So that's quite a characteristic feature of such a search algorithm.